Alrighty, looks like we have a follow-up to yesterday's deal. Appropriately hard, but maybe I can just use yesterday's solution. There exist two undirected trees and m nodes with n and m nodes labeled 0 to n-1 and 0 to n-1 respectively. You're given 2D integer array edges of length n-1, m-1 respectively, where edges of I denotes A and B nodes that are connected. Here, it doesn't seem that there's a... Okay, so yeah, it's undirected. Yeah. Node U is target to node V if the number of edges on the path of U to V is even. Note that the node is always target to itself. Okay. Return array of integers answers where answer if I is the maximum possible number of nodes that are target to node I of the first tree if you had to connect one node of the first tree to another node of the second tree. So this is the same deal as yesterday, where you can somehow connect the two trees using any arbitrary node to any other node. Here, it doesn't look like you're looking for distance from nodes, but just even distances or number of nodes within that are even without kind of bound. So I think this seems to be that you would always want to connect to the same node in the second tree. That provides you with kind of an additional maximum number of even type nodes. Actually, is that right? That's not right, actually. You might want to connect to separate. No, let's see. If you connect to a particular node in the second tree, that node in the second tree will provide you with some additional even nodes. Yeah, it's some constant additional even nodes. Okay, so I think I can start by trying to reproduce my previous answer, which is I start by creating, well, I guess I can probably start by doing kind of trivial cases. Is there any trivial case? Yesterday's trivial case was like k is equal to 1 or k equals 0. I guess here the trivial case is if you have no nodes or if you have no edges. Let's see, n is 2, the number of edges is 1. The number of edges is 1. What was the trivial case last time was k equals 0. I guess there might not be a trivial case this time. Okay, so let's go ahead and define it. So the key thing here is I want to just modify yesterday's solution such that if I am given a tree, I can return the number of nodes that are a certain distance away or an even distance away from any given node. Actually, maybe an even or odd distance away from any given node. Okay, so define, let's say, tree counter. And this is going to be given a tree based on the edges. And I'm going to say even count. That's going to be a boolean. Maybe I should write this in Python 3. Edges is going to be a list of integers, and edges is going to be a boolean. Is boolean bool in Python, and this should return a list of integers for okay, so given a list of edges for a tree and say is even boolean given a list of return all, return count of number of nodes, count of either even or odd count of nodes that are even or odd distance from each node in a list. So that means that n, my syntax is bad. N is going to be the number of nodes, which is the length of edges plus 1. And then I'm going to make a graph, which in this case will be, I'll make it as a matrix of sets. Yeah, I make it this as a matrix. So the graph is going to be a 2D array, or it's going to be a list of sets of neighbors for whatever in range of n. Graph is, okay, for each node, which will be an index in this list. Associate with set of neighbors, basically adjacent via an edge in edges list. So for every edge AB in edges, graph of A adds B, graph of B adds A. And I kind of want a copy of it at some point, but I'll save that for later. And recreating the okay, what is this? So okay, so I have my graph, and I need to keep track of the counts. So the connected counts will be for each node. I'm going to say it starts at 0, and I want to track the number of nodes that are x away from every node. That are x away for each node. Yeah, so it's going to be 0. I'm going to assume that it might be the maximum distance would be the maximum distance would be n, maybe n minus 1. I could make this into a set, or make this into a dynamic list. No, I think it's fine. Let's say connected, so it's going to be at most n away, most n minus 1 away. I'm going to say n for so um, so connected is going to be up to n, and then it's going to be for every node, and yeah, for every node and n actually, for each node in range n. And then I want a deck as well, double-ended queue that starts with my leaves. So actually I could probably detect which elements are my leaves by removing from the set of all nodes that actually, so let's add to deck, add to queue all leaves, which is nodes with one neighbor. So for every node in the range n, if the length of the graph of that node is equal to 1, then add it to the queue. Okay. And then while the deck exists, then what I want to do is I want to have a set of processed nodes and also a stack of process nodes, so I track the order of processing. So I'm going to go through and starting with the leaves, say Oh my lord. Okay. While there are nodes on the queue, so node equals queue dot pop deck pop left, and if the node has not been processed, so if it's processed already, then continue. Otherwise, processed is going to add this node, and the p stack will append this node. So I want to go through each leaf and increase the neighbors count based on this current node. Increase the neighbors like other nodes. So for each value from 0 to, so for each distance, I'll say d for distance in the range of n if, actually every node is a distance 0 away from itself, and that needs to be a part connected. So for each node in range n, the length add to queue all leaves, also make set each node distance 0 distance count to 1, since it's a distance of 0 from itself. So graph this node at distance 0 is equal to 1. So for every distance in range n, I think actually in range n minus 1 can't actually be equal to n. It might be n minus 2. As long, let's see, if there are nodes at this distance, or if there aren't any nodes at this distance, then that means that there can't be any further nodes. So if the connected to this node at this distance is equal to 0, then stop. Otherwise, for every neighbor in the graph of this node connected to this neighbor at distance plus 1 is added by connected to this node at that distance. So if I'm at this leaf and there's one node that's 0 away from it, which is itself, that means for the neighbor of it, there's going to be one additional node that is 1 distance away. And then if I had these two leaves, when 5 gets processed, it's going to increment 4's distance 1 nodes by 1, and 6 is also going to increase 4's distance node by 1. And if there are other stuff, then it's going to, like there are further stuff down here, that's like 1 away from 5, that's going to be 2 away from 4. So there's that. And also I need to remove this node from the neighbors group of nodes. So neighbor dot discard the graph of the neighbor, discard this node. of the neighbor discard this node. And also, I only want to process things that are currently leaves. So if the node is in process, continue. If the graph of this node, the length of the graph of this node is not equal to 1. Then do this later. So cross dec.append this node to be processed later, and then continue. Only process when node itself is a leaf. So for instance, I do 5. I don't process 4 until I finish processing 6, and when 5 and 6 gets processed, they remove themselves as neighbors of 4. So when 4 gets processed, it considers itself a leaf if it only has one neighbor, something that's further up or further into the tree. And then you remove yourself from the neighbor set. Okay, so that climbs up the tree or inwards in the graph until you're left with there's probably only one neighbor at this point. So maybe I should have done it the other way around for every neighbor in the graphic node. And then, yeah, like this, for every neighbor in the graphic node, and then for every distance. Every distance connected with the neighbor at that distance. Yeah, maybe that's fine. Wonder which way makes more sense. For every distance, and then for every neighbor, or for every neighbor and then distance? I think it's probably equivalent, no? Every distance. If it's 0, then break. And then every neighbor versus for every neighbor. I don't want to remove it multiple times, right? Yeah. I want to do it this way because this removal of the neighbor will make sense inside the for loop inside the distance loop. Okay. So that's doing it one way. And then doing it the other way is I'm going to go through the stack. So while the process stack is this, take the node from the stack, pstack.pop, and I'm going to say that if this node is so it's going to go through and say that the last thing that's processed is 1. So it's going to pop 1 off the stack, and then it's going to look at the neighbors. and if it's doing the neighbors, then it's going to be 0. And 0 only does stuff that's related to if this node is not in processed. Actually, let me pull up what I did yesterday. So process discard. So you immediately remove it from the process, and the neighbor should not be in process any longer. Yeah, okay. Maybe I should duplicate this tab. Here's the thing. Okay, so I remove it from the process. Processed, set, discard this node, and then for every neighbor in the graph of this node, and I need to have a copy of this thing, copy of the previous graph. So I'm going to say copy is also set, and do the same thing for the copy A, add B, copy B, add A, and I'll, after I messed around with the first iteration, say that the graph is now set to the copy version. Okay. No, that's not the set. Right here, copy is equal to the graph, or graph is equal to copy. So for every neighbor in the graph node, if the neighbor is not in process, then continue. Because process is stuff that is below a given node and has yet to be correctly processed. If it's not in process, then it's like above it in the tree and it already has accounted for it. So if the neighbor is not in process, continue. And then for I'll eventually need to add the neighbor to my no, I don't need to add it to the stack. It's already somewhere in the stack, further up. I think I just need to say that for every distance in range of, I think the highest distance might be n minus 1, the lowest distance might be 0, decrementing. If there are any things connected to this node at this distance is equal to 0, then skip it. Otherwise, actually, let's say, yeah. Otherwise, I'm going to say connected to the neighbor, add distance plus 1 is increased by connected to this node at this distance minus connected to the neighbor at distance minus 1. I think that's it. Double checking, so starting at distance minus 2, going down to 0, negative 1, distance minus 2. distance minus 2 there was actually n minus 2 here. And then after this loop is done, if I have at least 2 nodes, then I can say that connected of the neighbor at a distance of 1 is increased by 1. Pretty sure. Connected to neighbor at a distance of 1 is increased by 1, yeah. The nodes is greater than 1. And after I'm done processing the stack at that point, I should have the correct amount of distances away from each node, the correct amount of counts of each of the number of nodes away from each other node. So if is even, then I want to go through the 2D array of connected nodes and do a count for each node. Then actually, what's the way to handle this succinctly? You can say counts is going to be an array starting with 0 for each of the n nodes, and then for n in range, what? For index in for node in range of n, and then for index in range of n divided by 2. Let's say offset is 1 if 0 if is even, else it's 1. Then I'm going to do the sum of the nodes at this index. Actually, for every node, and this is maybe distance in range of 0 plus offset up to n going up by 2. Counts of this node plus equals number connected to that node at that distance. So distance would be like 0, 2, 4, 8, all the way up to the number of nodes. And similarly for an odd offset, it'd be like 1, 3, 1, 3, 5, so on. And then I return the counts. And I think I'm going to try to see if this runs at all now. So let's say return, or let's say print tree counter for edges 1 true, return 0. It's probably going to crash multiple points. Okay, if neighbor is not processed, line 49. If neighbor not in process. Is even is missing as a tree argument. Okay, yeah, I miscalled that. It's supposed to be edges, comma, true, close parentheses. Set does not support item assignment. I see. Graph of 0 assigned to 1. I think this should be connected to the node. Okay, so is this correct? So doesn't look like it. This is saying that for each of the 5 nodes in the first tree, the number of even nodes is 1. The number of even nodes is definitely not 1. Connected number of neighbor nodes at this distance. For each neighbor in the graph, the neighbors non-process continue. Each distance. Okay, so let's go ahead and just do a small comparison here. Seems right. Okay, so let's go ahead and just print out the number connected on the first strip. See if that's correct. So number connected to 0 at distance. Connected to 0 should be, so it does 1, 3, 4, which does 1, 2. So 1 goes to 0, so there's 0's, there's 1 away from itself, 1 is 1 away from 0, and then 1 is a leaf, so only 1 is done there, so 1 is 0 away from itself. 2 is going to have 2 will have 2 should have 3 here, I think. Okay, let me double check here. Let me print out the connected and the stack of processed. So what was the order of operations? So processed, oh boy, 1, 3, 4. Didn't add the nodes. It should have all 5 nodes in there, but it only has 1, 3, 4. So it doesn't add the neighbor nodes to the processed queue. Oh, I see. Yeah. For each neighbor in the graph node, once you do this, you actually do need to add the neighbor node to the process. Add it to the queue, so deck.append the neighbor. Oh boy, it went infinite. Deck appends neighbor. Why would that cause it to go infinite? Deck append the neighbor here. The graph neighbor, discard this node. Graph neighbor, discard this node. Deck appends the neighbor. It's probably going from here somehow. If the length of the graph node is not equal to 1, that appends the node later on. Oh, it's here is greater than 1. Let's see. It could be 0, I think. Yeah, there's a possibility that the length of the neighbor is 0 for the very final one. Connected is not defined. On line 57, misspelled. Connected. Okay, so it has something. Okay, that's the processing node. So 1, 3, 4, and then it did 0, 2. And it's at that 1. The number of things that are even away from 1 is going to be this one's 1, this one's 0 away. This one's 2 away. No, this is a 0. Number of things that's even away from 0. 1, 2, 3. Even away from 1 is 1, 2. Even away from 2 is going to be 1, 2. Even away from 3 is going to be 1, 2, 3. Even away from 4 is going to be 1, 2, 3. Okay, so this is all correct. Okay, and then let's go ahead and say it's false. So the number of things that are odd away from each node. From 0, there's 2 things that are odd away from it. For 1, there's 1, 3 things. For 2, there's 1, 2, 3 things. 3, it's going to be those 2, and 4 is going to be those 2, so that's all fine. Okay, so it looks good there. The tree counter worked. So the fixed amount that you can maximally increase account for any node to another node in the second tree would be you try to find the maximum for any odd distance away from any node in the second tree. Because if you have an odd maximum, then you connect something from the first tree to that node, which would be like the first edge, and then odd away from there would be even number away from the first tree node. So fixed max best increase would be equal to the maximum that you get if you tree counted edges 2 using an odd count, and then your answer array is going to be your answer array is just going to be your tree counter of 4 edges. Actually, this is just tree 2, edges tree 1 with true, and then for every index in range, and answer at the index plus equals the best increase, and return the answer. On line 70. I don't think I actually define what n is. N is the number of edges in the first tree. Which number of nodes in the first tree is number of edges plus 1. Okay. Get rid of the printout. see how this goes. Going too slowly. Is the timing up? Time limit exceeded. Huh. Interesting. Time limit exceeded. How big are these trees? 10 to the 5th? I was really hoping that this was not going to be too slow. So, I think if it was the case where let's speed this up. So let me go ahead and just do this last case and see if it actually answered it correctly by itself, or does it take too long to answer it? Looks like by itself it takes too long. Yeah, it just takes too long. So why is there any output? Oh, I thought I removed all my prints. Oh, output is what I returned. Interesting. It's a bunch of the same values. It's a bunch of the same values. Oh, you know what? Oh, yeah. Your answer is always going to be between one of two things, right? Because it's either an even or odd node. Your answer is always going to be returning one of two things. So, yeah, 87788 366. Seem to imply that I don't need to actually keep track of things a certain number away. Right, I just need to keep track of whether or not it's an even or odd. Even or odd node. And then on the second tree I need to keep track of whether or not the even or odds are bigger, because then you can always connect to whichever one makes it bigger. Huh. I guess this is maybe I'm just doing too much work. So if I started with any node, then I can, if I started with any node, arbitrarily say that node is even, then anything that matches it, anything that is even would be part of that. Okay, let me, okay. I think this is all maybe unnecessary. And if this answer is based on this, then I'm surprised that this would be labeled hard. It's just based on counting even odds. So how to count? I think I still need a graph. Say edges is in tree counter, and guess I still want is even. I don't even know. I think actually I don't. Edges. I think I just returned two elements, even versus the odd. So I'm going to make a graph, which is, I'm going to make a graph which is the set of neighbors for everything in the range of n, where n is the number of nodes, which is equal to length of edges plus 1. I'll still do for every a, b, and edges, graph of a dot append b, graph of b dot append a. And I just need to go through it like breadth first search. Breadth first search. Counting even and odds. So I'm actually going to say the deck starts out with just the first node, 0. Do I care about using a deck? Yeah, I do care about using a deck. And while the deck is this, yeah. So I'm gonna assume that 0 starts out as like, so it's almost like I'm going through the tree, coloring red and black. So I'll start with, say this is red, and then I'll put all the neighbors to this thing to be black, and then I'll put all the neighbors to that to be red. And since I know I'm alternating, then I'm going to say evens, actually let's say counts is a list of 0, 0. And then I'm going to say I'm going to is even is currently going to be parity is currently going to be 0 now. So I have a deck, and size is the length of the deck, which is going to be amount of active nodes with the current parity. So I'm going to start by saying the parity could be like red or red black 0 1. This can be 0 for 0, and then I'm going to set parity to become 1 for all the neighbors of it, and set the parity back to 0 for all the neighbors of that. So I should also have a scene set, and it should be just starting with 0. So for everything in size, so for everything on the deck, what I do is I pop off the deck, and I add the neighbors to the node. Add the neighbors. Actually, maybe I say scene dot add this node here. Yeah, maybe I say scene is just an empty set here. And then for every neighbor in the graph of this node, if the neighbor is not in scene, then the neighbor is added to the deck. Deck.add, the queue adds this neighbor, and then that's it. And then maybe the size increments the current counts for the parity. Counts for this parity is incremented by the size. And then technically at this point I change the parity as well. Parity is equal to 1 minus parity. Okay, so I start by saying 0 is colored 0 color red, or red is 0 and black is 1. And I add the neighbors to 0, which is 1, 2. Because they're not in scene. And then the next time it does the loop, looks at the size of it, and parity changes to 1. 1 minus 0 is 1. And then next time it does the loop, then it looks at the size of the queue, and that's going to be 2. And so it's going to increment the counts of the other parity to be 2. And then for every neighbor, and then it's going to go through and process 1 and 2, adding the neighbors of 1, 2 that are not already done. So 1, it's already done everything, but 2, it's going to add 3 and 4. Yeah. And then at the very end, I just return the parities. I return the counts. Let's go ahead and just print out the tree counter for tree 1, edges 1. That should not have append. That's correct, it should be add. That should not be add, it should be append. Okay, so here it's 3 and 2. So if 0 starts out as kind of evens, 0, 3, 4 is all the same, so it's going to be 3. 1, 2 is going to be odd, so it's 2. Okay, that is correct. Print the tree counter for edges 2. The other one is 3, 5. So 0. If that's even, then it's going to be 1, 2, 3. And if the other one's odd, then it's going to be 1, 1, 2, 3, 4, 5. Okay, that's perfect. So I think what I do here is I say that my answer array is going to be 4. So I'm going to take the maximum amount for the second one, the maximum amount for the second one, plus, and then whatever, and if it's even, then I use the 0 index 1 in tree counter, and if it's odd, then I use the odd one. So that's not actually correct, right? Yeah, that's not correct, because 0, I need to keep track of which ones are even, which ones are odd. I see. Because here 0 is even, 1 is even, and 2 is even. But in a different setup, then 1 could be somewhere else. Okay. So I know that 0 is always even in this counting. Okay, so I think what I need here is actually evens is a set. Even set. And actually, I say evens is going to be equal to a set, and I know 0 is part of it. Odds. No, I think what I could do is actually I could say I could just have a set of evens, and I know that 0 is part of it. And then whenever I do parity stuff, if the current parity is 0, then it's evens. Actually, so maybe evens it's an empty set. If the current parity is 0, then I add this set to another set. Evens dot add deck. I wonder if that works actually. So I'm going to go ahead and print out the evens before I return counts, or as I turn counts. Yeah, it's not hashable. Parity is 0, then I need to add all the elements to it. Or I can add the current parity to an index. Add the current. So let's see, parity tracker. Parity tracker is 0 times the number of nodes. And then when I pop a node, I say the parity tracker for that node is equal to the current parity. parity tracker. Okay. Okay, so 0 is even, 1, 2 is odd, 3, 4 is even, 0 is even, 1, 2, 3 is odd, 4 is even, 7 is even, 5, 6 is odd. That's correct. So when I return counts, I return not counts, I guess. I return an array that is for every node in range n, the array for this node is going to equal, I use the parity tracker, this node, as the index into the counts array and a return array. Out of bounds. Really? Parity tracker for this node should be 0, 1. I think. Unless node is the issue. Oh yeah, should be 0 times the length of n. Okay, so I think that why didn't this? Okay, actually that's right. So 3, 2, 2, 3, 3. That's, and then you increase those by 5. So the answer is going to be equal to the tree counter for edges of 1, where the fixed best increase from the second tree is going to be the maximum of tree counter for edges of 2, and add that to every value in the answer in edges 1 for every index in range. Length of edges 1 plus 1. Actually, let me just create variable n is equal to length of edges 1 plus 1. And for everything there, answer for this index increased by the best increase. Return the answer. Tree counter, that is not how you call this function. Okay. And it's running in 7 milliseconds instead of the extremely long one of the previous attempt. Huh. Okay. Is there a way that I could have done this faster? So I created my graph. I created a deck. Did I need to create a deck? Could I have created a... Yeah, I think I needed a deck. I need to remove stuff that were more recent, or the earliest ones, add onto it the neighbors and not process the neighbors. I guess I could alternate sets if I wanted to. Then I do the counts. I guess I could have done, I just could have done a parity tracker, and then at the very end summed up the parity tracker to get the number of ones that were odds, and then the evens is n minus that. So maybe I didn't have to track counts. But did I? The counts increasing the parity size. It's just not that. Doesn't take that long. Scene, add the node. Change the parity. I feel like this is pretty fast. Scene as a set. You do need to create a graph. That's strictly necessary. You do need to track which parity you're at. Some form of fashion. I mean, you could turn. Maybe you could, for each node in range n, maybe this is an extra bit here. You could reuse the parity array. So you could say this parity array is just parity tracker, and just reuse that same space and say parity tracker for this node is equal to counts of the parity tracker for this node. So if it's 0, then it becomes the counts of evens, and if it's odd, it becomes the counts of odd. And then return the parity tracker. It uses slightly less space. And you don't have to create the array. I guess the other thing is, if you're going through the second tree, you don't really need to worry about which nodes are at which parity. You just need to worry about which are the evens and what are the odds. So it could have been slightly faster without having to track that. So you remove the helper function and make separate functions for that. It actually went slower this time. It went slower, it used more memory. Oh my lord. Okay, I think I'm good with this. Yeah, I think I'm good with this. This is actually a much easier thing than yesterday's deal, because you just need to count odds and evens. Okay. So for the summary here, this boils down to assume that nodes are colored red or say black or white. basically have a parity where adjacent nodes are different color. The count of nodes that are even away will equal the total counts of nodes that match its parity. So for instance, if you were to just color this thing as red and black, or white and black, or this thing is white and black, or this thing is white and black, where again no two connections, or you match the zero with white with the black, or black with the white, but you can't do black black. The number of blacks is the number of things that are even away from all blacks, and the number of whites is the number of even things from away from all whites. That felt a little funny saying that, but so determine, so for tree 1, assume node 0 is, say, 0, which is parity black, is parity 0 black. Determine use a queue, a deck in Python that starts with only node 0 and does a breadth first search, going through alternating neighbor layers, alternating neighbor levels, layers, adding the size of the layer to the counts of that parity, and any unadded, unseen neighbors to the next layer in the queue until queue is empty. So this is this thing right here. So you start with a deck. Deck is initially just 0, and then look at the current size. That's the current number of things of this particular color's parity. Increase either the counts of 0 parity or the count of 1 parity. You have a specific for loop that goes through everything that's currently there, popping it from the deck, adding it to the scene, tracking the parity of that particular node, because that's also necessary later on. And then for every neighbor with that node, if it's not already been done, then add it to the queue. And then finally changing the parity back to, or switching the parity. This can be done within Boolean, like true false, but this is kind of a hack to make it also be used as index into the counts array. For tree 2, also track the parity for any node, so 0, 1 in an array. Return an array of size where each node has the count of its parity at the node's index in the array. nodes index in the array. For tree 2, simply find the maximum number of odds or even parity, and which will be added to node or tree 1's array as the answer. So the answer is going to be the number of parity for tree 1 for each node, the count of the nodes of the same parity for that node, plus either like all the evens of the other one or all the odds of the other ones, because depending on where you connect it, you can get those other ones to be of even or odd length away, or even the length away from this node. So yeah, time complexity, this should be O of n. O of n. You need to go through each node exactly once. You need to go through each node exactly once. I mean, it's O of n plus m to determine the counts slash base complexity. This is going to be O of n as well for tracking which nodes are what parity, and also for the deck can be at like at most n size, I guess, if like one node is connected to all of the nodes. All right.